Welcome to another session of Everyday Mathematics. Today we continue with the MIT Integration B Qualifying Exams 2010. And we're looking at problem 3, problem 4, and problem 5. So I hope you stay locked and you get to see what we're doing. The third problem happens to be the indefinite integral of x plus 1 squared times x minus 1 to the power third. The fourth problem is the indefinite integral of x times the natural logarithm of 1 plus 1 over x. And the fifth problem that here was the definite integral from x equals to 0 to x equals to 1 of sine squared natural logarithm of x. So these are our problems today. I hope you do enjoy, and if you have any comment, any question, please feel free to get back to us with them. Problem 3, as we said, was the indefinite integral of x plus 1 squared times x minus 1 to the power third. The first thing one may want to do is to first of all let y equals to x minus 1, right? And what that means is that dy dx equals to 1. And so if you multiply both sides by dx, that means that dy can be substituted for dx. And then since y equals to x minus 1, well, that means that y plus 2 equals to x plus 1. And we're targeting this part of the integral. So now pulling y and plugging in y in place of x minus 1, we have y. In place of x plus 1, we have y plus 2. So this becomes y plus 2 squared times y to the power third. And when you expand this part here, what you get is y squared plus 4y plus 4. And then you multiply y to the power third across the cube root over y, and so you get y to the power 7 over 3 plus 4y to the power 4 over 3 plus 4y to the power a third. And so since we have that, now the integral of this is 1 over the exponent increased by 1 over 1 plus 7 over 3 y to the power 1 plus 7 over 3 plus 4 over 1 plus 4 over 3 y to the power 1 plus 4 over 3 plus 1 plus 4 over 1 plus 1 over 3 y to the power 1 plus a third plus the integration constant. And so when you simplify these, 3 plus 7, 10, and 3 goes up, so 3 over 10, y to the power 10 over 3, plus 12 over 7, y to the power 7 over 3, plus 12 over 4, y to the power 4 over 3, plus integration constant. Now, since we said y equals to x minus 1, that means that the integral of x plus 1 squared times x minus 1 to the power third is the same as 3 over 10, and then in place of y we plug in x minus 1, so 3 over 10, x minus 1, 10 over 3, plus 12 over 7 times x minus 1 to the power 7 over 3 plus 3 times x minus 1, 4 over 3 plus the integration constant. And this here is the final answer. Okay, so if you have any questions to that end, please feel free to leave us a comment or just any contribution or suggestion in the comment section. So the next problem happens to be the indefinite integral of x times natural logarithm of 1 plus 1 over x. So first thing I would do personally is I would multiply x both the numerator and denominator. so that we have the integral of x times natural logarithm of x plus 1 over x in place of this part here. So what then happens is that now we could use the rules of logs, and so that means the quotient here is the same as the difference of the actual functions here. The quotient within the log function means that we can get the difference of the logs of both the numerator and denominator. So this log x plus 1 over x is same as log x plus 1 minus log x, so multiply x across, and so we have the integration of x times natural logarithm of x plus 1 minus x times natural logarithm of x. We're going to use integration by parts, so the strategy I've adopted here is by saying, okay, how do we handle the x's and how do we handle the logs? But before that, I needed to separate this into two separate integrals. X is the same as half the derivative of x squared, and we're going to see how that is important. And we keep natural logarithm x plus 1 as it is, and then this x also is the same as half the derivative of x squared. So keeping on what we have here, we can use integration by parts, where if you have the product of u and dv dx, when you integrate that, that's the same as uv minus the integral of v, the product of the integral of the product of v and du dx. So in this instance here, this part here happens to be something like that, right? And so our v definitely is half x squared, and our u is log x plus 1. And then here our v will obviously be half x squared and u log x plus 1, as we've just mentioned. So our two integrals here now can be handled in the following manner. The first integral I have put under the curly brackets, so we have half x squared log x plus 1 for uv minus half x squared times 1 over x plus 1, which this is the derivative of log x plus 1. The second integral, again half x squared log x minus half x squared, and the derivative du dx in this situation here is 1 over x. So going forward, we have half x squared log x plus 1 minus half x minus 1 plus 1 over x plus 1. Now you may be wondering why this comes to be this way. So it's just that if I have x squared and I have x plus 1 as a denominator, the first thing I could do is just multiply by x, and we have x squared minus plus x, sorry, rather, and then so we have negative x here, and then if we multiply by 1, we have negative x minus 1, and so we have 1 remainder. So here we have the dividend is x minus 1, and the remainder is 1 over x. So this is what our polynomial results. Now this is something very easy to integrate, but also at the same time here we see x squared when divided by x results into just a simple x. So these parts here are already integrated, and the important part here is that now we have to integrate x, which is x squared over 2, and multiply by this half again, so it becomes a quarter x squared, right? Keeping the signs minus here in the same way. And then 1 here is the same as x, and with this half it becomes now plus, because we have negative and negative here. So we have half x. And then the integral of 1 over x plus 1 is natural logarithm of x plus 1, keeping the negative and this positive under consideration, becomes negative log x plus 1. And then obviously here it remains as it is, and here integral of x is the same as x squared over 2 times a half, so it becomes a quarter x squared. So we'll see that this and this will cancel because they have opposite signs, and then we can now merge this part and this part, and so that becomes now half x squared log x plus 1 minus log x, and so again we can use the rules of logarithm where you have the difference of the log functions is the same as the division of the items under the log function, plus a half x here and then minus a half log x plus 1. Now we forgot to bring this half here, and that's why it's showing up here. Okay, and this is the answer that was provided. Okay, so if you have any questions, feel free to reach out, and we'll be very, very glad to get back to you. So our next problem, that's problem number 5 rather. Which is the definite integral from x equals 0 to x equals to 1 of the sine squared natural logarithm of x. So personally, just would like to substitute for log x and say let u be equal to log natural logarithm of x. So that means that du dx is the same as 1 over x, and that means that you can substitute for dx with the product of x and du. And so what is x? Using this expression here, x is definitely equal to e to the power u, right? And so we can now say e to the power u du is equals to, could be substituted for dx. And now the important bit here is that now this integral of ours here, it's very important to see that as x tends to 0, u would tend to negative infinity. As x tends to 1, u tends to 0. And that's why we have here negative infinity at the lower limit and 0 at the upper limit. Sine squared, we have u in place of log x and eu du in place of dx. So we want to play around with the sign here by letting u equal to negative u. That results in this negative at the upper limit becoming positive, and since we have sine squared u, sine negative u is negative sine u, but because we're squaring that, sine squared negative u is the same as sine squared u. And then obviously e to the power u, the u becomes negative, and since du becomes negative when we substitute the negative u in place of u, then this negative shows up here. And so we can now flip the limits so that that negative sign disappears, and so we have e to the power negative u sine squared u as our integrand. Now it's important to know that when you have cosine 2u, that's the same as 1 minus 2 sine squared u, such that sine squared u is equals to 1 minus cosine 2u over 2, right? And so we can now plug this in place of sine squared u there. So our integral now becomes the integral from u equals to 0 to u tending to infinity of e to the power negative u times 1 minus cosine 2u over 2. And so we can play around. So we have e to the power negative u here minus e to the power negative u times cosine 2u, and we pull half out. And a lot of people would want to use probably integration by parts. For me, that kind of is painful. So what I would do is I would just express this in terms of Euler's expression, which is e to the power I 2u plus e to the power negative I 2u over 2. And so that when I combine everything together, I have the integral from a half times the integral from u equals to 0 to infinity of e to the power negative u minus e to the power negative 1. This is a plus here. The power, this negative 1 is here because I'm pulling u out in the bracket here, out of the bracket, and then this positive I2u remains there, and the I obviously is the imaginary unit. The same thing here, the negative 1 is there, and then negative I2u is this negative I2 because now we're pulling 2u out, and that is out. So we can keep going. The important part there is that now we have the u's, and when we integrate everything, integrate e to the power negative u is the same as negative e to the power negative u minus a half the integration of e to the power negative 1 plus 2 plus I2 close bracket u is the same as that over negative 1 plus 2i, because this is the constant up there, and then the same thing for the second part. And now as limit as u tends to infinity for the upper limit, we see that this part goes to 0. This part also goes to 0 because this e to the power negative 1 u, e to the power negative u, as u tends to infinity, that part tends to 0. And the same part, this part goes to 0. It's only, so this entire part goes to 0. This part, if we call it big U, limit goes to 0 at the upper limit. Now, limit as u tends to 0 of u, it means that this becomes negative 1, and since we're subtracting the negative limit, we're removing the lower limit substituted in, it means that now this becomes positive 1, and then this part here goes to 1, this part goes to 1. So what essentially we have is important. We have 1 plus a half, open bracket, this half here, because we're subtracting, and because there's a plus here, so we have 1 over negative, let me just delete this, so that we can see what we're doing here. So we have a half 1 plus 1 over 2 times 1 over negative 1 minus 2i plus 1 over negative 1 plus 2i, right? And as we continue, we can now multiply these denominators together. So we have 1 plus a half negative 1 minus 2i times negative 1 plus 2i is the same as, so it's the difference of two squares. We have negative 1 squared minus 2i squared. And then at the top, we're just adding the 2, and quickly we see that this one and this one cancel. So we are left with negative 2, and this one here is positive 1, and this is negative 4, so it becomes plus 4 very quickly. And so we have now a half in bracket 1 plus a half negative 2 over 5, and what that means is that we still have half here plus 1 half times 1 plus half is negative 2 arising from up here, would cancel with that, and so we have a half in bracket 1 minus 1 over 5, and 5 times 1, 5 minus 1 is 4, so we have 4 over 5, and this becomes by 1 by 2, and this becomes 2 over 5. And this is the final answer that was provided. And that is it. So yeah, if you have any questions, please feel free to reach out again. Kind of sounds like a broken record, but we are very keen. We're curious to interact with you and share our passion of math with you. Until next time, bye bye.